Hi, everybody. It's Professor Mitchell. Today we're starting Chapter 2, beginning with Section 2.1 on systems of linear equations with unique solutions. In this section, we'll look at the diagonal form of a system of equations. We'll look at elementary row operations, 1, 2, and 3. We'll look at the Gaussian elimination method, the matrix form of an equation. We will not use spreadsheets to solve systems. A system of equations is in diagonal form if each variable appears only in one equation and only one variable appears in an equation. Here's an example. X equals 50, Y equals 125, and Z equals 50. So you can see why this system of equations is called diagonal, because the only terms to the left of the equal signs are right here along this diagonal. And from a system of equations that's in this form, it's very easy to read off the solution. In this system of equations, X is 50, Y is 125, and Z is 50. So in order to put systems of equations into diagonal form, we're going to use elementary row operations. These are operations on the equations or rows of a system that alters the system but does not change the solutions. Elementary row operations are often used to transform a system of equations into a diagonal system whose solution is simple to determine. So the first elementary row operation is just to interchange any two equations. So for example, in this system of equations, it turns out it's a good idea to rearrange the equations so that all of the equations containing X are on top. So in this case, we can simply switch the first equation with the third equation. So that would be an example of using elementary row operation 1. Notice the notation that we use to indicate that we're doing that. R1 stands for row 1, R3 stands for row 3, and then we just use this double-headed arrow to indicate that we are swapping those two rows. So after we perform that row operation, we end up with this new system, which is equivalent to the old system. It has the exact same equations in it, just in a different order. And that brings us to elementary row operation 2, which is to multiply an equation by a non-zero number. So hopefully you remember from algebra that if you multiply both sides of an equation by a non-zero number, it gives you an equivalent equation. That's an equation that has the same solutions. So in this case, what we want to do is multiply the first row of the system by some number that will make the coefficient of X into a 1. So to show you this one, I'm going to switch over to the tablet. Here we go. All right. So again, we want to take that 6x and make it into an x. So to do that, we're just going to multiply both sides of the equation by 1/6. So that 1/6 is going to get distributed. Remember to do it to both sides. And the notation that we're going to use for this is going to look like 1/6 times R1. All right. The new system we're going to get out of that is going to look like 1/6 times 6x is x. 1/6 times minus z is minus 1/6 z. And then 3 times 1/6 is 3/6, but I'll simplify that to 1/2. All right, so that's the only equation that changes using this row operation. I'm going to leave the other two rows just the way they are. we'll be changing those later. All right, so after performing elementary row operation number 2, we end up with this system. All right, let's go back to the presentation and talk about elementary row operation number 3. I feel like this is the one we use the most. Elementary row operation number 3 is to change an equation by adding to it a multiple of another equation. This is how we eliminate certain variables from certain equations to make it look more like diagonal form. All right, so for example, let's go back to the system that we just ended up with. And what we're going to do in this example is we're going to add a multiple of one row to another to change that system so that only the first equation has an x term. In other words, we want to get rid of this 3x. So once again, let's go back to the tablet. Now, this particular row operation takes a little getting used to. All right, so what we're going to do, we want to get rid of this 3x. And so what we're going to do is change row 2 by adding to it a multiple of row 1. And in this case, what would get rid of the 3x is a negative 3x. If we were able to add 3x plus negative 3x, that would eliminate that x variable. So what we're going to do is add row 2 to negative 3 times row 1. Okay. So what I'm going to do, and hopefully after you get used to this, you won't feel the need to do this every single time. I am going to write, I'll just scribble up here, what does it look like after I multiply row 1 by negative 3? I would get negative 3x. And then over here, I would get negative 3 times negative 1/6 z. So negative 3 times negative 1/6 is positive 3/6. In other words, positive 1/2. And then 1/2 times negative 3 is negative 3/2. Okay, so that is negative 3 times row 1. To do this row operation, we are going to add that to row 2. Okay, add these two together. Come on now. All right, so we're leaving the first equation alone. We like that equation just the way it is. X minus 1/6z equals 1/2. But we're going to have a new row 2. And row 2 is going to come from adding these two together. So that's going to go negative 3x plus 3x cancels. That's the whole point. And then here we have 0 plus negative y is negative y. 1/2 z plus z. So the coefficients we're adding are 1/2 plus 1. 1/2 plus 1 is 1.5, or 3/2. So 3/2 z. And then negative 3/2 plus 6. So here we need a common denominator. Negative 3/2 plus 6. We're going to think of that as negative 3/2 plus 12/2. Negative 3/2 plus 12/2 is 9/2. All right, and we are not doing anything to the third equation. So after doing this elementary row operation, row 2 plus negative 3 times row 1, we end up with this system of equations. So notice that only the first row at this point has an x in it. All right. Remember, we're working towards putting the system in diagonal form. So now what we want to do is continue on and do that to the y column, make it so that the only y is in the second equation, and then make it so that the only z is in the third equation. So So let's go back to the presentation for a minute, and then that is exactly what we will do next. All right, so this is the same thing that we ended up with. All right, so what you've been seeing here is steps in what's called the Gaussian elimination method. The Gaussian elimination method transforms a system of linear equations into diagonal form by repeated applications of the three elementary row operations, which again are number one, rearrange the equations in any order. Typically, you want to start with an X term in the top left corner. Number two, multiply an equation by a non-zero number. And finally, number three, change an equation by adding to it a multiple of another equation. All right, so as I mentioned a moment ago, the next example is we're going to continue what we started with the previous examples. So now they're just saying continue Gaussian elimination to transform this system into diagonal form. So they're not going to tell us which row operations to use. That's the way it's going to work in general. You're just going to figure it out. But there is a certain rhythm to it. There are certain steps that you always do in the same order. So hopefully this example will start to give you a feel for that. And then we'll be doing many, many examples of these. And you will really get it down. You'll practically be able to do it in your sleep. All right, so let's go back to the tablet. And here's where we are so far. So we have the X column just the way we want it. So now we're going to continue. So the next big step is this second column, the one with the Y's. We want to make it so that only the only Y in that column is in the second row. All right. So the first step is let's multiply the second row by -1. And that's going to give us the same row 1. However, row 2 now, everybody's being multiplied by -1. So now that's going to be Y minus 3/2 Z equals -9/2. And we're not changing the third row. In this step, we're not changing the third row. However, the next step is going to be to eliminate this Y. Now, normally what I will do is I'll leave the next page blank and just go to the next page. I did not think to do that this time. So what I'm going to do is just erase this and I'll continue up here. Okay, so we are in this next step changing row 3. And the way that we're going to change row 3 is by adding -1 times row 2. You can also think of this as row 3 minus row 2. Okay, so again, only changing row 3. So we're going to keep row 1 just the way it is. We're going to keep row 2 just the way it is. Okay, but now, again, think of it as row 3 minus row 2. So Y minus Y cancels, that leaves 0. Z minus -3/2 Z. So you have to be careful. Think of that as what you're doing to the coefficients. So 1 minus -3/2, which is the same thing as 1 plus 3/2. 1 plus 3/2 is 5/2. So that's going to be 5/2 Z. And then over on this side, we have 0 minus -9/2. 0 minus -9/2 is the same thing as 0 plus 9/2. So that would give us 9/2. Okay. All right, so now the Y column is just the way I want it. Remember, we're trying to get this thing into diagonal form. So the X column is just the way I want it. The Y column is just the way I want it. Now I need to get the Z